Reality number 1. Quantum Many Worlds Interpretation. 1957. Princeton graduate student Hugh Everett proposed something revolutionary in his doctoral thesis, a new way to understand quantum mechanics that eliminated the need for wave function collapse. Standard quantum mechanics says particles exist in superposition, multiple states simultaneously. When you observe them, the wave function collapses. The particle chooses one state. Randomness determines which. Everett said no. The wave function doesn't collapse. All possibilities happen, but in different branches of reality. When you measure a particle's spin, it doesn't randomly choose up or down. It goes both ways. The universe splits. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes are real. Both versions of you exist, each experiencing a different result. This is called the many worlds interpretation. It sounds absurd, but it solves major problems in quantum mechanics. It eliminates randomness, makes quantum theory deterministic, explains why we never see superposition at macro scales. Here's why it's taken seriously. Quantum mechanics is the most accurately tested theory in physics. Its predictions match experiments to extraordinary precision. But the standard interpretation has philosophical problems. The many worlds version provides mathematical elegance. Does this mean alternate realities exist? Not necessarily. Many worlds might just be mathematical formalism, a way to calculate outcomes, not a literal description of reality branching. But here's what disturbs me. If many worlds is correct, then every quantum interaction creates countless new branches. The number of parallel universes is incomprehensibly vast and constantly growing. Every decision you make, every particle interaction, every moment, splits reality. In some branches, you made different choices, lived different lives, died earlier, never existed. In infinite variations, the many worlds interpretation is now mainstream physics, not fringe speculation. Major universities teach it, researchers use it, because mathematically it works. Does that make it true? We may never know. We can't observe other branches. We're trapped in our own timeline. But the mathematics demands they exist. Reality number 2. Parallel universe collision marks. 2015. Researchers at University College London analyzed data from the Planck satellite. It mapped the cosmic microwave background radiation, the leftover heat from the Big Bang. They noticed something odd. Unusual cold spots in the radiation, places where the temperature is slightly lower than surrounding areas. These spots are enormous. Supervoids, regions with fewer galaxies. Standard cosmology has trouble explaining the largest cold spots. They're bigger than models predict. The probability of them forming randomly is extremely low. Dr. Ranga Ramchari proposed an explanation. These cold spots might be scars, bruises where our universe collided with another universe. The impact left a mark in the cosmic microwave background. In multiverse theory, universes can exist adjacent to each other, like bubbles in foam. Sometimes bubbles touch. When they do, they exchange energy, create detectable signatures. If Cherry is right, we're looking at direct evidence of another universe, a parallel reality that existed long enough to brush against ours 14 billion years ago. Other physicists have proposed similar ideas. The axis of evil, an unusual alignment in the cosmic microwave background that seems to violate the cosmological principle. Some researchers suggest it's evidence of anisotropy caused by multiverse collision. Most scientists remain skeptical. The cold spots might have conventional explanations, statistical flukes, or effects we don't understand yet. Jumping to parallel universes is premature. But here's what I can't ignore. The mathematics of eternal inflation predicts multiple universes. Our observable universe is just one bubble in an infinite foam. Those bubbles can collide, and collisions would leave exactly the signatures we're finding. The evidence isn't conclusive, but it's there. Anomalies in the cosmic microwave background, patterns that don't fit single universe models, signatures that make sense if parallel realities exist. We may be looking at the first observational evidence that our universe isn't alone. that other realities exist beyond the cosmic horizon, and sometimes they touch ours. Reality number 3, Delayed Choice Quantum Eraser, 2000. Physicists Yoon-ho Kim, R.U., S.P. Kulik, Y.H. Shi, and Marlon Scully published results of the Delayed Choice Quantum Eraser experiment. It demonstrated something disturbing about reality. The experiment uses entangled photons. Send one through a double-slit apparatus. Send its twin a different direction. Measure the twin. The measurement determines whether you see interference patterns or particle patterns in the first photon. Here's the twist. You can make the measurement after the first photon has already hit the detector. Your choice of what to measure in the future affects results that happened in the past. This violates our understanding of causality. Effects shouldn't precede their causes, but in this experiment, they do. Retrocausality, the future influencing the past. One interpretation. When you measure the twin photon, you're not changing what happened. You're choosing which reality you observe. The photon went through both slits in one timeline, went through one slit in another timeline. Your measurement selects which timeline you experience. Multiple realities exist simultaneously. Your observations determine which branch you're in, but you're not creating reality. You're choosing among realities that already exist. This experiment has been repeated many times. The results are consistent. Whatever interpretation you prefer, the data shows that quantum measurements can apparently affect past events. Or, equivalently, multiple histories coexist until observation selects one. Reality number 4, Simulation Argument, 2003. Oxford philosopher Nick Bostrom published a paper proposing that we might be living in a computer simulation. His argument is logical, not speculative. Consider 3 propositions. First, civilizations reach technological maturity and develop the ability to create detailed simulations. Second, mature civilizations want to run ancestor simulations, simulating their own history. Third, we're almost certainly living in one of those simulations. If the first 2 are true, the third follows necessarily, because a mature civilization could run millions or billions of ancestor simulations. If this happens, the vast majority of conscious beings exist inside simulations, not base reality. The probability that you're in base reality becomes vanishingly small. Almost everyone experiencing a universe like ours is simulated. This creates an alternate reality in a different sense. Our universe might not be the original. We might be digital copies, living in a programmed environment, governed by rules set by programmers in a higher reality. How would we know? If the simulation is detailed enough, we couldn't tell. Everything we measure would be simulated. Physical laws would be code. Quantum mechanics might be the simulation's rendering engine. The Planck scale might be the pixel size. Some researchers have proposed tests. Look for glitches in the simulation, anomalies that shouldn't exist in a perfect physical universe. The double-slit experiment might be a rendering optimization, only calculating details when observed. Elon Musk famously argued, there's a 1 in billions chance we're in base reality. If civilization doesn't destroy itself and continues advancing, eventually we'll create perfect simulations. Then simulated beings outnumber real ones by factors too large to comprehend. This doesn't prove we're simulated, but it raises the possibility that our reality is secondary, that a more fundamental reality exists beyond ours, that we're characters in someone else's universe. Reality number 5. String theory, Branes. String theory proposes that fundamental particles aren't point-like. They're tiny vibrating strings. Different vibration modes produce different particles. Electrons, quarks, photons, all just strings vibrating differently. For the mathematics to work, string theory requires extra dimensions, not just the 3 space dimensions and 1 time dimension we experience. String theory needs 10 or 11 total dimensions. Where are these extra dimensions? Compactified, curled up so small we can't detect them. Like a garden hose viewed from far away looks one-dimensional, but up close has circular dimensions. In some versions of string theory, our universe exists on a 3-dimensional brane. a membrane floating in higher dimensional space. Multiple branes can exist, each one a separate universe, with its own physical laws, its own particles, its own timeline. These branes can interact. When they collide, they release energy. Some physicists propose that Big Bangs are caused by brane collisions. Our universe's beginning might have been one brane smashing into another. If brane theory is correct, parallel universes aren't just hypothetical, they're geometric necessity. Other three-dimensional branes exist in the higher dimensional bulk. We can't see them because they're separated in directions we can't access. But gravity is special. In string theory, gravitons can travel through all dimensions. This might explain why gravity is so much weaker than other forces. Most of its strength leaks into other dimensions. If gravity crosses between branes, then theoretically information could too. Or, under extreme conditions, matter might tunnel between branes, moving from one universe to another. This remains speculative. String theory hasn't been experimentally verified. We don't have evidence of extra dimensions or branes, but the mathematics is elegant, and it naturally produces multiple universes as a side effect. Reality number 6. Quantum Immortality Thought Experiment. 1987. Physicist Hans Moravec proposed a disturbing thought experiment, an extension of the many worlds interpretation. Imagine you're connected to a quantum device. It measures a particle's spin. Spin up, you live. Spin down, you die instantly and painlessly. In many worlds, the universe splits. In one branch, spin up. You survive. In another branch, spin down. You die. But here's the twist. In the branch where you die, you cease to experience anything. You can't observe that timeline. The only branch where your consciousness continues is the one where you survive. From your subjective experience, you always survive, no matter how many times you run the experiment. Even if the probability of survival is 1 in a million, you only experience the timelines where you live. This is quantum immortality. From your perspective, you're invulnerable. Every lethal quantum event splits reality. You die in some branches, but you only experience the branches where you survive. Now consider, all death-causing events involve quantum processes. Neurons firing, chemical reactions, molecular interactions, every near-miss car accident, every bullet that narrowly misses, every disease that randomly doesn't kill you. If many worlds is true, and if consciousness only experiences branches where it continues, then from your subjective perspective, you're immortal. You'll always find yourself in the branch where you survived. However improbable, other people die in your timeline, but from their perspective, they're still alive in another timeline. You cease to exist in their branches, but you're alive in yours. This has disturbing implications. You might be the only version of yourself still experiencing reality. All other branches diverged long ago. Or maybe you're one of countless versions, each thinking they're unique. The thought experiment is meant to highlight problems with many worlds, but some researchers take it seriously. As a literal possibility, that consciousness selects survivable timelines. It can't be tested. By definition, you only experience your own continuing timeline. But it suggests that alternate realities aren't just theoretical. They might be the reason you're still here. Reality number 7. Afshar Experiment Paradox. 2004. Iranian-American physicist Shahryar Afshar conducted an experiment that seemed to violate complementarity, one of quantum mechanics' fundamental principles. Complementarity says you can measure wave properties or particle properties, never both simultaneously. If you detect which slit a photon goes through, you lose interference. If you see interference, you can't know which path. Afshar's experiment claimed to violate this. He placed wire grids at the dark fringes of an interference pattern, then used lenses to determine which slit photons came from. According to his analysis, he measured both properties simultaneously. If correct, this challenges how we understand quantum mechanics, and it has implications for alternate realities. One interpretation: the photon travels through both slits in one reality and one slit in another reality. The wire grids interact with one reality, The lenses interact with another. By carefully arranging the experiment, Afshar accessed both realities simultaneously. Other physicists disputed Afshar's interpretation. They argued he didn't truly measure wave and particle properties at the same time. The debate continues. But the experiment raises a possibility. Under specific conditions, information from alternate quantum histories might be simultaneously accessible. We're not switching between realities. We're observing multiple realities at once. Reality number 8. Wheeler's Participatory Universe. John Archibald Wheeler was one of the 20th century's most influential physicists. He coined the terms black hole and wormhole. Late in his career, he proposed something radical. Wheeler suggested that observers don't just measure reality, they participate in creating it. The universe doesn't exist in a definite state until observed. Observations aren't passive. They're active selections among possibilities. In Wheeler's view, the past isn't fixed until we observe evidence of it. When we look at light from distant stars, we're not seeing what happened. We're determining what happened. This connects to alternate realities through the delayed choice experiment. If observation determines past events, then multiple pasts exist, each consistent with current observations. We select among them by measuring. Wheeler proposed the participatory anthropic principle. The universe requires observers to exist, not just to perceive it, to actualize it. Consciousness plays a fundamental role in reality. If this is true, then alternate realities are the default state. Every possibility exists in superposition. Observers collapse them into single histories. But different observers might collapse them differently. You and I might be experiencing slightly different paths, both consistent with present evidence, both equally real. Our observations created these histories retroactively. This sounds like philosophy, but Wheeler grounded it in quantum mechanics. The mathematics supports multiple histories. Observations select among them. If consciousness is doing the selecting, then reality becomes deeply strange. Reality number 9. Evidence from quantum computing. Quantum computers exploit superposition and entanglement to perform calculations. A quantum bit exists in multiple states simultaneously. Many qubits create an exponentially large computation space. David Deutsch, pioneer of quantum computing, argues that quantum computers prove the existence of parallel universes. Here's why. A quantum computer with 300 qubits can explore 2 to the power of 300 possible states simultaneously. That's more states than there are particles in the observable universe. Where is this computation happening? If our universe contains only the qubits we observe, there isn't enough computational substrate. The calculation requires more physical resources than exist in our reality. Deutsch's explanation: the computation is distributed across parallel universes. Each universe handles a small part. The quantum algorithm coordinates them. The answer emerges from a massive parallel calculation spanning countless realities. When you run a quantum algorithm, you're not just processing information in our universe. You're leveraging computational resources from parallel timelines. The interference patterns that give you the answer come from alternate versions of the calculation. This interpretation is controversial. Other physicists argue quantum computers don't prove parallel universes. The computation might occur in mathematical space, not physical reality. But the resource argument is compelling. Quantum computers achieve results that seem to require more than our universe contains. Either the computation is non-local in time and space, or it's distributed across multiple realities. Every time a quantum computer runs, it might be proving that alternate realities exist, and that we can use them for practical purposes. Reality number 10. Mandela effect as reality shifts. We covered this extensively in Day 15, but it connects to alternate realities in a specific way. The Mandela effect isn't just misremembered facts. It might be evidence of timeline merging. If many worlds is correct, universes constantly branch. But what if they can also merge? Under specific conditions, similar timelines might recombine. When they do, people from different branches end up in the same timeline. Some remember one version of history, others remember a slightly different version, not because memory is faulty, but because they came from alternate timelines that merged. The specifics they disagree on are points where the timelines diverged. Berenstain versus Berenstein, Mandela dying in prison, or 2013, fruit of the loom cornucopia. These aren't mistakes, they're scars from timeline mergers. This hypothesis is unprovable, but it explains patterns, why certain memories are shared by large groups, why the changes are specific and consistent, why no photographic or documentary evidence exists for the alternate versions. If true, then the Mandela effect proves we experience multiple realities, not sequentially, but merged together. Our timeline is a combination of branches that split and recombined throughout history,